So the next talk is by Emily Nardoni, and she's going to talk from n equals to 2 supersymmetry to adjoint QCD.
Okay, thank you very much to the organizers for the invitation to speak at this very nice conference. Today I'm going to tell you about a body of work that I've been pursuing over the course of the pandemic, some of which is upcoming. And this is done with my fantastic collaborators, Eric Doker, Thomas Dumitrescu, and Efrat Gershkovitz. So gaining insight into the strong coupling dynamics of gauge theories, such as confinement and chiral symmetry breaking, is of course a very challenging but important problem. Today I'm going to tell you about some new perspectives we have on this problem in the realm of non-supersymmetric gauge theories. In particular, I'm going to tell you about some insights we've learned in recent years on the class of theories, which goes under the heading of adjoint QCD in 4 dimensions. So this is a class of 4-dimensional gauge theories with Val fermions that transform in the adjoint representation of the gauge group. And for my purposes today, I am exclusively talking about the NF equals to 2 case, so 2 adjoint Val fermions, and gauge group SUN. So this is a class of gauge theories labeled by an integer n, which goes like the rank of the gauge group. Now, this is a tale of supersymmetry breaking. So my approach is going to be to softly break n equals to 2 supersymmetry. And one of the key highlights is that the many detailed properties of the n equals to 2 gauge theory are going to play a crucial role in this story and are going to conspire in interesting ways to determine the predicted IR phase of this non-supersymmetric gauge theory. Furthermore, this analysis is going to both depend on and motivate new results in n equals to 2 gauge theory, so there's this nice positive feedback loop between these 2 subjects that I'd like to highlight throughout this talk. So let me begin by telling you what we might expect the IR dynamics of adjoint QCD to be, and how we're going to probe this expectation using n equals to 2 supersymmetry. So standard lore for chiral gauge theories as applied to NF equals to 2 adjoint QCD would posit that the fermion bilinear condenses, and this leads to the properties of confinement and chiral symmetry breaking. So in this conjectured scenario, the chiral symmetry breaking pattern would be that a continuous SU NF equals to 2 chiral symmetry, which is the SU2R symmetry of the n equals to 2 theory in our analysis, would be broken by this condensate to its U1 Cartan subgroup. The 2 Nambu-Goldstone bosons from this chiral symmetry breaking pattern would parameterize a CP1 nonlinear sigma model. Furthermore, there's a discrete Z4n R symmetry, which would be broken to a Z4 subgroup. And so there would actually be n copies of the CP1 vacuum related by the Zn action. So I'll refer to this phase, this conjectured phase throughout this talk as the CP1 phase of adjoint QCD. In this phase, the Zn one-form center symmetry is unbroken and so features confinement. So a few important comments are in order. Firstly, the Vafa-Witten theorem applies to NF equals to 2 adjoint QCD since the 2 Val fermions can compile into a Dirac fermion. And so this leads to some constraints on the dynamics. Firstly, that the U1 Cartan of the SU NF equals to 2 continuous chiral symmetry must remain unbroken in whatever phase is actually realized by this theory. And this is, of course, consistent with this conjectured CP1 phase. The next comment is that these CP1 vacua are close to the n vacua of n equals to 1 super Yang-Mills in 4 dimensions. So what I mean is that by adding a small, even infinitesimal fermion mass deformation to the CP1 vacua, they all become exactly degenerate and lead exactly to the n confining and chiral symmetry breaking vacua of 40 n equals to 1 super Yang-Mills. In fact, there are going to be several very nice parallels between the story I'm telling you today, going from n equals 2 to adjoint QCD, and the n equals 2 origin of confinement in the n equals to 1 vacua. And this fact of the proximity of the CP1 vacua to the n equals to 1 vacua is part of the intuition behind some of these nice parallels. Okay, so our strategy follows from the following observation that we can interpolate between n equals to 2 super Yang-Mills in 4 dimensions with a G gauge group, but again, here I am exclusively talking about SUN gauge group. and the non-supersymmetric NF equals to 2 adjoint QCD in the IR by adding a particular supersymmetry breaking operator, which is a non-holomorphic mass for the vector multiplet scalars of the n equals to 2 theory. In this RG flow, the two fermions in the IR are exactly the n equals to 2 gauginos. And importantly, this supersymmetry breaking operator preserves all symmetries of both our upstairs supersymmetric theory and downstairs non-supersymmetric theory, except for supersymmetry itself. And so in particular, all anomalies are automatically matched between the two theories. And so this motivates the question of whether we can use this supersymmetric embedding to explore the IR dynamics of this non-supersymmetric gauge theory. And of course, I'm telling you the answer is yes, and it's yes because of some key pieces of leverage we have in this analysis. So firstly, this supersymmetry breaking operator, this non-holomorphic mass for the vector multiplet scalars, lies in a protected multiplet of supersymmetry. It is the bottom component of the n equals to 2 stress tensor multiplet, and as such, it can be tracked on the moduli space of the n equals to 2 theory. Doing so, it is matched to the Kähler potential on the Coulomb branch. So this is the n equals to 2 Kähler potential, which is a globally defined function given in terms of the periods of the SUN generalization of the Seiberg-Witten solution to the n equals to 2 theory. So the next comment is that for our supersymmetry breaking scale M small compared to the relevant strong coupling scale in the problem, we can then reliably analyze this deformation as a deformation to the n equals to 2 effective action given by the SUN Seiberg-Witten solution. And one comment on this is that this analysis really does require the entire n equals to 2 effective action, so not just the Kähler potential, but the holomorphic couplings and et cetera, all the data, all the non-perturbative data. Now, of course, we would like to extrapolate to the large M regime, the large supersymmetry breaking regime where we make contact with adjoint QCD, but this is the regime where this soft supersymmetry breaking analysis is no longer reliable. Instead, one of our key results that I'm going to tell you about is that we're able to construct a dual description of the physics that's valid, or we argue is valid for this regime, that is deduced from softly broken Seiberg-Witten theory, and which interpolates between this small m regime, reliable regime, and the large M regime, which makes contact with adjoint QCD. And this dual description is going to lead to a compelling qualitative picture of the dynamics as a function of M, and ultimately, one of the punchlines is it will predict the CP1 phase of adjoint QCD. So this brings me to part 2. Now we're going to discuss the supersymmetry breaking analysis in the small m regime. And so in particular, I need to tell you the properties of this Kähler potential, which is our supersymmetry breaking operator we're adding to the theory. So let's start with SU2. In SU2, the Kähler potential is a function of a single complex modulus, and it's a known function, which I've plotted in the complex U-plane on this slide. In particular, it is convex, and it has a single minimum at the origin of moduli space where U equals 0. I've also shown on this plot the monopole and Dion singular points of the SU2 moduli space, and these points lie on the boundary of the region where the Kähler potential is negative. So our minimum at the origin lies at negative k, and the k equals 0 contour is plotted here in black. And in fact, this k equals 0 contour is exactly the wall of coincides with the wall of marginal stability in SU2, which encloses the strong coupling chamber of moduli space, wherein lies our minimum. Now, in the generalization to SUN, the periods are now functions of n-1 complex coordinates, and they're given in terms of period integrals holomorphic period integrals in the SUN Seiberg-Witten solution. Explicit integrated functions whose properties we can determine and plot, for example, are only known for SU2 and SU3 when these are given in terms of Gauss hypergeometric functions and Appel F4 functions, respectively. So, motivated by this analysis, we did a computation and obtained a simple all-order Taylor series expansion for the ANA dual periods of SUN Seiberg-Witten theory around the origin of moduli space. And so the result is an expansion whose coefficients can ultimately be reduced as basically monomials of simple functions, gamma functions, trigonometric functions. And so this is very nice. It reduces, of course, to the hypergeometric functions in Apple F4 functions and SU2 and SU3, and can be thought of as an n-1 indexed family of generalizations to these functions. So using this result from the previous slide, as well as a variety of other analytic and numerical analyses, we studied the structure of the SUN Kähler potential. And of course, the generalization of the picture I showed you for SU2 is rather complicated for SUN, but the main punchline is that we've collected evidence that the SU2 picture remains qualitatively correct. So here I'm showing some of these features with a numerical plot for SU3 in some slices of moduli space. And as in SU2, we have a minimum at the origin of moduli space where the Kähler potential is negative. It scales like minus n squared. Its value can, of course, be computed explicitly. And surrounding this region at the origin is a region of negative Kähler potential. And the multi-monopole points, which are the SUN generalization of the SU2 monopole and Dion points, lie on the boundary of this region of negative K. So I'll remind you, the multi-monopole points are the endpoints in moduli space where a maximal number of n-1 mutually local Dions become massless at once. So you can also visualize in this right-hand side plot this core strong coupling region close to the origin. So this is a picture of the extrapolation of this k equals 0 contour up in the other direction of moduli space. Okay, so we'd like to study the physics of this small m vacuum at the origin of moduli space, and let me tell you the answer. So our supersymmetry breaking potential is only going to give a mass to the scalars in the theory. So in particular, this is going to be a phase with order n massless gauge fields and fermions. This vacuum is in the Coulomb phase, and the entire chiral symmetry, SU2 times Z4n symmetry, is unbroken. So this is the analysis that is reliable at small m, but indeed this would be quite a surprising prediction for the IR dynamics of adjoint QCD. So one takeaway from this analysis is that if adjoint QCD does confine and break chiral symmetry, then the true vacuum will require at least one phase transition away from this reliable small m vacuum. Now, a clue as to how we might proceed and capture some of this physics as we dial up the supersymmetry breaking scale m comes from taking into account the massive BPS spectrum in this vacuum at the origin. So this is what I'll explain now. So in the SUN strong coupling chamber of moduli space, wherein lies our small m minimum, the stable BPS spectrum consists of n towers of n-1 mutually local Dions. These towers are rotated by a Zn inside the Z4n discrete R symmetry. And at the origin, their masses follow a sign law. So the lightest of these stable BPS states have a mass of order the strong coupling scale over n, and the heaviest have a mass of order the strong coupling scale. So this first BPS level constitutes the cutoff of our EFT, after which we've stopped including all of the relevant physics, and so our description is no longer reliable. And in particular, this minimum we've described at the origin of moduli space is not going to be reliable above this cutoff. However, we have a very important piece of information, which is that, in fact, one state from each of these towers, each of these n-1 towers, comes down and becomes massless exactly at each of the n multi-monopole points. So at these points, these are the n-1 light Dions participating in the effective physics. And this suggests the following strategy, that we use the effective field theory that describes the dynamics of these light monopoles as a dual description to capture the physics of these massive BPS states at the origin that we know we're going to encounter as we dial up the supersymmetry breaking scale. And we can do this using the dual description at one multi-monopole point because the rest are related by the Zn, so action of the Zn, and we'll recover the rest of the BPS states. So that's going to be our philosophy going forward. And so let me tell you some of the properties of this dual description at the multi-monopole points. So the effective field theory at these points is an abelian Higgs model with n-1 abelian gauge group factors, and it consists of n-1 vector multiplets, abelian vector multiplets, whose scalars are identified with the A-dual periods of Seiberg-Witten theory, the ones that vanish at the multi-monopole points. And furthermore, n-1 electrically charged hypermultiplets that are fundamentals of the SU2R symmetry and correspond to our light monopoles in the theory. So then the name of the game is to add our supersymmetry breaking deformation to this effective action and study its dynamics. And so now our supersymmetry breaking deformation is going to match onto the Kähler potential that I was plotting earlier upon integrating out the monopoles. So upon integrating out these light hypermultiplets in the effective theory. So now we have to do a matching computation to compute this potential. And so the whole scalar potential of this model is going to consist of both the supersymmetric quartic D terms of the abelian, n equals 2 abelian Higgs theory, and the supersymmetry breaking piece. So now let me tell you some of the main features of this model that are going to lead to some of the interesting physics. So firstly, there is a matrix, an n-1 by n-1 matrix of effective gauge couplings in the model. I'm denoting it by this T matrix here. And the main feature I would like to point out is that the couplings have threshold corrections from massive BPS states at these points that haven't been included in the light physics. And the detailed structure of these threshold corrections is very interesting and leads to interesting predictions for the dynamics. So as you can see here, they vary in an interesting way over the matrix and have interesting n scalings. One important point is they, in particular, couple all of the U1 dual gauge groups in this effective description. And so because these were very important objects for us, we actually computed them. So we computed them using a purely n equals to 2 analysis of the Seiberg-Witten periods near the multi-monopole points on the moduli space. And so this is another nice example where this SUSY breaking motivation led to some interesting result telling us about the structure of Seiberg-Witten theory. So let me point out the key features of this scalar potential. So firstly, let's look at the supersymmetry breaking part. There's this linear term in the abelian vector multiplet scalars that has this nice sign here. And this is a tadpole, which comes from matching onto the Kähler potential away from the multi-monopole points. So I'm matching onto this convex slope at the multi-monopole points, and that's why I get this tadpole. Secondly, there are positive definite masses for the abelian vector multiplet scalars. And this is, of course, expected. Remember that this operator started its life giving a mass to the UV vector multiplet scalars. Next, this operator gives tachyonic masses to the monopole fields, to these hypermultiplet scalars. And so this minus sign in front of the quadratic monopole terms is going to make these monopole fields want to condense in this model. And of course, this is very important for the dynamics. Another nice feature is that the supersymmetric D terms in the EFT take the form of a ferromagnetic spin chain. So the couplings in this spin, you can show that the couplings in this spin chain are determined by the off-diagonal elements of the inverse matrix of effective gauge couplings in this theory. And it's a non-trivial fact that you can show of this matrix that these are negative. And so what this means is that the spins in this spin chain want to align, but more specifically, the monopole field VEVs, when they get VEVs, are going to want to align in SU2R space. So this is going to have consequences for the chiral symmetry breaking pattern. Okay, great. So this leads me to my final part of my talk, which I want to tell you the result of doing this soft supersymmetry breaking analysis in this dual EFT near the multi-monopole points. And so I'll tell you the results. So the main result can be summarized as we find a cascade of first-order phase transitions as we dial up the supersymmetry breaking mass scale m. So at small m, only the vector multiplet scalars get VEVs, the monopole fields do not condense. And we find a Coulomb phase, which approximates the Coulomb phase of the supersymmetric theory and is, of course, consistent with our previous small m analysis. This is an important consistency check on this description. However, something interesting happens as I increase m, this vacuum becomes unstable, and instead, the monopole field vevs want to turn on, and they activate pairwise, so more and more pairs turn on, in a series of first-order phase transitions. So this is exactly jiving with our intuition that in this dual effective description, the new physics is coming from these monopole fields wanting to participate in the dynamics. And these phase transition points approximately track the levels of the massive BPS states that I showed you earlier in this vacuum at the origin of moduli space. This, again, also is a nicely consistent picture of how the new physics is coming in higher and higher, at higher and higher values of the supersymmetry breaking scale. Interestingly, a robust feature of every one of these Higgs phases as a function of m is that we obtain this predicted chiral symmetry breaking pattern of SU2R to U1. And this is due to this fact about the D terms that I pointed out. And so importantly, every phase is consistent with the Vafa-Witten theorem for adjoint QCD, although I emphasize that the Vafa-Witten theorem does not apply to this softly broken supersymmetric model, and so this is a non-trivial output of our procedure. Then by the time I reach large M, all the monopoles condense, and I have a stable vacuum which reaches out to m goes to infinity with the following properties. So when one of these hypermultiplet field vevs condenses, its corresponding U1 dual gauge group is Higgs, under which it's electrically charged in this effective description. And so when all of the monopoles condense, what you see is that the Zn one-form center symmetry is unbroken and the phase is confining. Furthermore, all fluctuations about this vacuum get a mass, except for the two Nambu-Goldstone bosons from the chiral symmetry breaking pattern. And the reason everything else gets a mass is precisely because of these off-diagonal couplings between all of the gauge group factors. And so we get a CP1 vacuum. There are, in fact, n CP1 vacua related by this Zn, one copy at each multi-monopole point, so we exactly reproduce these predicted features of the CP1 phase. So let me summarize that this soft supersymmetry breaking model of by adding the soft supersymmetry breaking deformation to Seiberg-Witten theory has predicted in this large M phase the CP1 phase of adjoint QCD. And I've told you so far in this talk about several interesting properties of this phase and how they come out of the supersymmetry breaking procedure. So I've told you about confinement and the continuous chiral symmetry breaking pattern and the massless spectrum in this predicted vacuum. However, there are many other interesting properties that you can extract from this model. And each one of these interesting properties comes from some detail of the n equals to 2 gauge theory. So in particular, you can extract the predicted discrete R symmetry breaking pattern. This is related to the symmetry relating the multi-monopole points. You can extract the predicted Z2 symmetry breaking patterns. So in particular, that at the end of the day, both charge conjugation and time reversal are preserved in this large M vacuum. And the breaking pattern we observe is in fact consistent with another constraint from the Vafa-Witten theorem for adjoint QCD. This is a nice output. And we can extract the large N scalings of various quantities in this theory, including the gaugino condensate and the vacuum energy, and we see that they have the right scalings to describe a theory with adjoints, and they come from these nice features of the n equals to 2 theory, including this structure of the gauge couplings. And in all cases, these match the predicted CP1 phase. So I guess with that, I'll leave up this slide, and thank you very much for your attention.
Thank you very much for this very clear talk. Are there any questions?
So what's the large n scaling? If you take the large n limit, what's the large n scaling of those massive fluctuations? Does it remain order 1?
Good. So there's a hierarchy of scales for the massive fluctuations. So some of them are lower and some of them are higher and get large then. Yeah, there's a hierarchy.
Okay.
So the pure SUN cyberweighting theory on its Coulomb branch also contains this strongly coupled Archer-Douglas point.
This strongly coupled.
Also contains the strongly coupled superconformal theory. This is Archer-Douglas type theory. Yeah. So if one tried to kind of mimic this kind of soft supersymmetry breaking type of deformation around that point, is it conceivable that there's a possible non-supersymmetric CFT that lives in IR?
I think this is a very interesting question. I've thought a bit about it, and we're thinking about it. So yes, I think this is a very interesting question to think about. Okay, like, well, what if I explore other points on the n equals to 2 moduli space? Of course, for the purposes of making contact with adjoint QCD, I motivated that these were really the points that capture the physics, but what about, okay, like, what could I get at the Argyros-Douglas points? I think it's very interesting. Just for reference, we of course checked where these land in this picture, and they land right in here, still inside the strong coupling region of SU3. So they're like right around. Well, I guess one of them will show up in this plot, but yeah, they're inside this strong coupling region.
Okay, Thank you.
Any other questions? Seems to be the case, so let's thank Emily again. A very nice talk.